Welcome to thermocatalytic CO2 conversion. In the process industry, most reactions are carried out using a catalyst, a material that speeds up the reaction. Such a catalyst can be activated by electricity or light, but the most widespread approach is using an elevated temperature, and this is called thermocatalysis. In this video, we will focus on processes using thermocatalysis and then especially processes to convert CO2 into useful chemicals. When you would make a touristic trip along different cities, there are typically several ways you can travel. Likewise, when you want to make certain chemicals, there are typically various routes to achieve this. This is what this slide illustrates. When starting with water and CO2 as building blocks, there are various ways to get useful products such as ethylene, methanol and kerosene. These routes can be partly based on electrochemical steps, which we will treat in the next lecture, and partly based on thermochemical steps. We will now more detailed look at those thermochemical steps. One important intermediate in this specific scheme, but also in the chemical industry in general, is syngas. It's a mixture of CO and hydrogen and can be used to make many different chemicals. The exact composition, the ratio of CO and hydrogen, the presence of other components, depends on how it is made, and what ratio is desirable depends on the process for which it is the feed. If, for example, it contains too much CO compared to hydrogen, this can be adjusted using the water gas shift reaction. Steam is then added to make more hydrogen at the cost of converting CO into less useful CO2. While this is an equilibrium reaction, the forward reaction is often referred to as the water gas shift, while the backward reaction is normally called the reverse water gas shift. In this graph, you can see that increasing the temperature is a way to push the equilibrium from the right to the left, meaning making more CO. The drawback of operating at lower temperature is that the reaction will run slower. Once you have syngas, you can make longer hydrocarbons from it, for example jet fuel, also called kerosene. This is done via the Fischer-Tropsch synthesis. Here you see the equation for this reaction, invented about a century ago, not surprisingly by two researchers named Fischer and Tropsch. For this reaction, you need roughly twice as many hydrogen as CO, especially when the symbol N is high, meaning large molecules. These large molecules are not formed in one go, but via several intermediate steps. In every step, there is a chance that the reaction stops and a relatively small molecule is released. This chance is determined by the chain growth probability called alpha, which can be tuned by several factors, but the temperature is an important one. In the plot on the right, you see clearly that the higher the chain growth probability alpha, the more large molecules you get. Kerosene is a mixture of various hydrocarbons, but an important portion is typically in the C10 to C12 range, so you need a rather high alpha to make it. Let's go back to our overview. Now we will focus on methanol. It can be used as a transportation fuel, but also serves as a precursor to make several other chemicals. It can be made from CO and hydrogen, syngas, or from CO2 and hydrogen, and that's a more desirable approach for the future. The current route from syngas is shown here. This reaction is typically accelerated by the catalyst shown here, a small couple particle in the nanometer scale on a carrying material called the support with some zinc oxide to make an optimum catalyst. This is currently already done in industry. As said, we would like to move to use CO2 instead of CO. However, the problem is that the nice catalyst shown here doesn't do well with water. And as you can see, we are producing water as a byproduct when we switch to CO2. So the challenge is to develop a catalyst that can cope with this. Worldwide, several research groups, including my own group, are working on this. That brings us already to the final slide. We have seen that there are many different ways to convert CO2 and water into useful chemicals. Quite often, syngas, the mixture of CO and hydrogen, is used as the intermediate. Routes can consist of thermochemical steps, electrochemical steps, or a combination of both. Current industrial processes mostly rely on thermochemical steps. This means that thermochemical CO2 conversion will be closest to practical implementation. This concludes the video. Thanks a lot for your attention.